In our previous class, we have discussed that one of the solution for critical section problem is a semaphore. Semaphore is a synchronization tool. It is an integer variable which has two indivisible operations or atomic operations known as wait and signal. Wait and signal are also called P and V operations. What is wait operation? Wait operation is wait of S is while S less than equals to 0, it doesn't do anything, it is spinning. If S is not less than equals to 0, then S minus minus and enter into the critical section. Similarly, while coming out, it must do the S plus plus. So do remember, whenever we are writing wait function, wait itself says that these all lines, while S less than 0, semicolon S minus minus, and where you are writing signal, it is actually S plus plus. And as we are saying, it is indivisible operation. A part of the code cannot be executed. Either all the instructions will execute or none. Correct? So these two has to be remembered. One is wait, another is signal operation. And these two operations can only be carried out on a semaphore. Semaphore means that integer variable. Here our integer variable is S. The semaphore is usually initialized to 1. Correct? So now we have discussed that there are two different types of semaphore are there. One is binary semaphore, another is counting semaphore. Binary semaphore is having two values 0 and 1. Binary semaphore is having value 0, 1, 1. These are called the mutex. Right? It is initialized to 1 actually. But counting semaphore says that the value is with a range of unrestricted domain. It can be 1, 2, 5, 10, 20 like that. You can have an integer value. So it is not binary value 0, 1, 1. So value can range over an unrestricted domain. So both the semaphore works on two things. One is wait, another is signal operation. In counting semaphore, if you are using wait, it decrements the count, and if it is signal, it increments the count. Correct? We have read up to this. Is it understood what is the difference between binary semaphore and counting semaphore? Anybody having doubt on binary and counting semaphore? Semaphore is just an integer variable. Binary semaphore means it has only 0, 1, 1. If it is counting semaphore, it can have any integer value over a unrestricted domain. So we have two different kinds of semaphore. With this, we'll go for solving one of the problem over here. Just look into this problem. Consider two concurrent processes, P1 and P2. There are two processes, P1 and P2. P1 process has a statement S1 and P2 has a statement S2. Try to understand. There are two processes. First process, P1 process has the statement S1. P2 process has the statement S2. Correct? We require the S1 to be executed before S2. S1 must execute first, then the S2. Is it understood what this question is asking for? It is saying that you must ensure that S1 to be executed before S2. So first S1 must execute, then S2. So what is the order in which you will put the semaphore so that it will ensure that S1 has executed first, then S2. Suppose we have taken a binary semaphore. Suppose we have taken a binary semaphore sync. We have taken a binary semaphore sync. You can take any name, give any name over here. Binary semaphore sync, and that is initialized to 0. Right? And this to be used by P1 and P2. It is given. So default value of sync binary semaphore is actually 1, but here it is initialized to 0, explicitly given that it is initialized to 0. So what will happen if I write in this way? What will happen? Suppose P1, P2 are there. P1 wants to execute. We want what? S1 to be executed first, then S2. So S1 will execute. While S1 will execute, at the same time, suppose P1 wants to execute, P2 wants to execute, it will go for this wait sync, right? Wait function, what it does? Wait function is this one. Wait function is while S less than 0. What is value of S now? S is 0, so it is waiting over here, spinning over here. So when the work of S1 is over and it will come out, it will invoke the signal function by incrementing the S. Once the value of S is incremented, this condition is false. And once this condition becomes false, it will enter into the critical section for executing S2 by decrementing the value of S. Correct? Suppose P2 will start executing before P1. Let P1, P2 are two processes. P2 will start executing before P1. What will happen? When P2 will start execute, it will go to wait. So it will go to wait first. What is the value of S? S is 0. So it will just spinning over here. It cannot come out. It will just spin over here only. Right? So even if the P2 will start executing first, it is just spinning over here. So whenever P1 will come, it doesn't have any wait over here. So P1 will execute directly S1. And while coming out, it will give signal sync so that this S++ will occur and S2 can continue its execution. Is it understood or anyone having doubt from this example? Is it understood or anyone having doubt? Here sync we have taken as the semaphore. The sync is whenever you are passing sync, actually the sync is being copied to S and this S is being executed over here. And this variable sync is shared by both process P1 and P2. Any doubt on this? Okay. Now we'll go for one more example of semaphore. Suppose we have 4 concurrent processes, P1, P2, P3, 4, P4. There are 4 processes are there, correct? And what we want, this is we have 4 processes. P1 is a process, P2, P3 and P4, right? And each process has also code. The code for P1, code for P2, P3, P4, all are there. Code for P1, P2, P3, P4 is there, correct? This has to be P3. The code of the processes are given. Now, what is the order in which you must give the wait and signal so that P2 and P3 can be started only after the completion of P1. So these two, P2 and P3, these two can only be started, P2 and P3 can only be started after the starting of P1. After the starting of P1, what is the order in which you will give so that P2 and P3 can start only after P1? So P1 definitely will execute first, then P2 and P3. So what you will do? What you will do over here? Just look into the previous example. I want S1 to be executed first before S2. So what we have given? S1 executed, then we have given signal. For P2 we have given wait. So what will do over here? I want the P1 to execute first, then the code of P2 and P3. So particularly for P2, what I will give? I want P1 to execute first before P2. So I give I take a semaphore over here, I give signal AB. And here I give wait AB. What is wait? Wait function already I told, while s less than equals to 0, semicolon, s minus minus. So if P2 wants to enter, it cannot enter into this code because it is initialized to 0. Because it is initialized to 0. So condition satisfies, it is spinning. Correct? So by writing these two, we ensure that P2 will execute, P1 will execute before P2 by writing these two codes. What is the semaphore we have taken? AB. AB is the semaphore we have taken. You can give any name, X also you can take. We give one semaphore variable over here, one semaphore variable over here, ensuring that P2 will execute after P1. I hope it is understood. Exactly in the same way, if I want P3 to be executed after P1, P1 should execute first. What I'll do? Similarly, exactly in the same way, I take another semaphore AC, assuming this is A and this is C. So a signal AC, and here I give wait AC. So wait AC means, what is AC? AC is initialized to 0. So as long as it is 0, it is just waiting over here. But this will enter into the code while coming out AC is incremented now until P3 can continue. By writing these two, so see over here, by writing these two, we ensure that P3 will execute after P1. It cannot execute before. Okay, only this line, last line of code you forget, only up to this. So I write code of P1, signal AB, signal AC. Here I give wait AB, code of P2, wait AC, code of P2. My first condition is satisfied or not? So P2 and P3 can be started only after the completion of P1. Only after the completion of P1. For the time being, just do not ignore these last two statements. For the time being, ignore the last two statements. I will tell you that what is the need of the last two statements. So by writing this, we ensure that P2 and P3 will execute after P1. Is it understood, or anyone having doubt? Anyone having doubt on this? Okay. Now we'll go for the next one. The second condition says that similarly, P4 can be started. P4 can be started only after the completion of P2 and P3. It requires that P4 can only start this P4. This P4 can only start after the completion of P2 and P3. What should I do then? P2 and P3 should complete, then the P4 should start. So what should I do? I have already done this part. P2 must start after P1. What I have done? I have given a signal over here and wait over here. Correct? Can anyone say that how will ensure that P4 will start before P2? Sorry, P2 must end, then only the P4 will execute. First P2, then P4. First P2, then P4. What should I do? Anyone? What should I do so that P2 will execute first, then P4 will execute? Anyone who can say? Is it understood or not? My objective is P2 must execute first, then the P4. So P4 will give a wait over here by taking an semaphore, and here I give a signal operation in P2. That means P2 will definitely execute. It doesn't have any restriction, but while coming out, it will increment the BD. Signal operation increments the BD. Wait operation, it will wait for BD is 0, so it will wait over there. The way we have given one semaphore, we have taken for P2 and P4. Similarly, we can take another semaphore so that P3 will execute before P4. This ensuring that P3 will execute before P4. So who is waiting, P4 is executing, P4 is waiting till the P2 or P3 has to complete. So we give a wait over here. So these variables, the weight of CD means CD is less than equals to 0. So it satisfies and it will be remaining or spinning in that loop. Is it understood? Or anyone having doubt? Is it understood from this slide? Hello?
Yes.
Now, what is the problem in semaphore? What is the disadvantages of semaphore? It says that all the time, unless it has not got the lock, it is just spinning over there or not. Till the time S is less than equals to 0, what it is doing? It is just spinning over here. It is just spinning over here. That means it is busy in waiting for the lock. It is busy in waiting for the lock. This is called the busy waiting. So processor is not doing any fruitful work or any useful work. It is just waiting to acquire the lock. So this concept is known as the busy waiting. This is an important short questions. Busy waiting. What is busy waiting? The processor is busy in acquiring the lock or getting the lock while not doing anything. When the process is in a critical section, any other process that tries to enter into this critical section must loop continuously in the entry code. Must loop continuously in the entry code. As it is continuously looping inside the entry code, so this is known as busy waiting. Or this semaphore is also known as spin lock. This is called busy waiting or spin lock. It spins while waiting for a lock. The process spins while waiting for the lock. Therefore, it is called the spin lock. The same concept, it is called the busy waiting, or this is known as the spin lock. Both the terms you remember. So spin lock or busy waiting is a problem, is a disadvantage for the semaphore. Correct? But semaphore ensures that no two processes can enter into the critical section at the same time. There is another way of implementing the semaphore with no busy waiting. Semaphore may be implemented with no busy waiting. So what we'll do over here, with each semaphore, there is associated a waiting queue. So for every semaphore, if you are taking, for every semaphore, we'll have a waiting queue. Each entry in a waiting queue has two items. So we'll have a structure kind of thing, which have two variables. One is value of an integer type. Second one is a pointer to the next record in the list. So it is a self-referential structure having two data members. One is the value. Second one is the pointer to the next record. Correct? And they have only two operations, block and wake up. They have only two operations, block and wake up. So where we'll put the block? Place the process invoking the operation on the appropriate waiting queue, and wake up means it will remove one process in the waiting queue and place it in the ready queue. I'll give an example so that you will understand. So what we are going to discuss? One of the problem is busy waiting. So can we have a semaphore implementation with no busy waiting? Yes, it can be. If you implement what? If you implement a waiting queue associated with each of the semaphore. And for that, we'll take a structure which will have two things. One is value, another is pointer to the next record. And this will have two functions, block and wake up. This can be understood over here. Very simple. We have a structure, we have integer value and a linked list which is pointing to the next one. Correct? So it is a self-referential structure. So what we do actually in wait operation, just remember the wait operation. Wait operation, what it does? Wait of s, while s less than equals to 0, semicolon, s minus minus. That is there in wait or not? Now we have modified it. Whenever a process will enter, so instead of waiting, a counter is there, s value will be decremented. So if s is 0, it will be decremented to -1, decremented to -2, -3, -1. Every process will come, it will decrement the value. Correct? If it is less than 0, that means if it is minus, that means it is waiting. See, if it is 0, it will enter. If it is minus minus, means definitely it is a negative value. If it is a negative value, we'll add the process to the list. We'll add the process to the linked list. And we'll invoke a block. And for those processes, we'll block them. Is it understood? Previously, one process will enter, other process will just spin in their while loop. Here they are not spinning, they are just blocked. And for those processes, for every processes, a value is being decremented. Every time a process will come, the value will decrement. Suppose my value, S value is 5. What does it mean? It means that 5 processes wants to enter and they have not got the chance because the minus minus operation has been done. So here the semaphore value can be negative. This is not a binary semaphore. Now it becomes a counting semaphore. It becomes a counting semaphore. So while coming out, what do we do over there? We invoke the signal operation. In the signal operation, what do we do? We give s plus plus only. But here what we'll do? We'll do s value plus plus. That means one of the process is selected. One is selected. But if it is 0, is s value is less than equals to 0, right? If it is less means some processes are there in the list. We'll take out one process from the list. And we invoke the wake up because we have blocked over here. So we'll have a wake up. So processes doesn't need to be waiting in the loop or spinning in the loop. They will be in the block state. Whenever a process will finish its execution and come out from the critical section, value is incremented and a wake up call is given so that another process will be selected and it will be given for the processing. Correct? So here the value of S can be negative, can be the semaphore value can be negative. So initial value of S is 1. We can take 1 over here. 1 minus minus this becomes 0. So that means this is the only first process. Correct? So if condition, see over here, S value is 1. 1 is less than equals to 0. It doesn't satisfy. If it doesn't satisfy, it will enter into the critical section. Suppose when the process in the critical section, next process will come. S value will become what? 0. 0 is less than 0. It is actually less than equals to over here. Because S value is 1. 1 minus is, sorry, it is 1. 1, it makes 0. 0 is less than 0, doesn't satisfy, it will come out. Then when the next process will go, it doesn't satisfy because it is 0. 0 minus minus will become 1. Minus 1. So minus 1 less than 0. Minus 1 less than 0. So it will add the process to the list. Any doubt? Any doubt from this? Is it understood? S value is initialized to 1. So as it is 1, decremented over here, this becomes 0. this becomes 0. So this condition doesn't satisfy, it will enter into the critical section. At the same time, if another process will come, this makes it -1. -1 satisfies, so it will be added to the list. Next process will come, it will make it -2. So it will be added to the list. Another process will come, it will make it minus, so it is -3, it will be added to the list. And like that, any number of processes will come, they will be added to the list. While coming out, when the first process has finished this execution, it will make it what? Plus means it will go for -3. So if it is less than 0, so it will remove it from the list and wake up. Similarly, for the next one, it will be -2. For the next one, it will be -1. Like that, it will go on every time it is being incremented till it becomes 0. Correct? So the value of semaphore with BG waiting is never negative. The value of semaphore with BG waiting is never negative. However, the value of semaphore without BG waiting, may be negative. Here we have seen the value of this is negative, but in semaphore without BG waiting, it is always positive. So if it is negative, the magnitude indicates the number of processes waiting on the semaphore. So if it is -4, that means 4 processes are waiting. Correct? If it is -10, that means 10 processes are waiting. So if are going for without BG waiting, then it may be the negative value will come. Otherwise, semaphore is always positive. We must guarantee that no two processes can execute wait and signal operation on the same semaphore at the same time. Correct? I hope this slide is understood, or anyone having doubt over here? So we'll have a small introduction to this deadlock and starvation. The detail about the deadlock, we have a separate topic, but look over here that we have just introducing what is a deadlock. If 2 or more processes are waiting indefinitely for an event, that can be caused by only one of the waiting processes. Just look over here, there are P0 and P12 processes. One is applying the wait operation on the semaphore S. Another is applying the wait operation on semaphore Q. After this, the P0 wants to apply the wait operation on Q, while the P wants to have to appear the wait operation on S. Correct? So, can you implement it? Can it be possible? Just a second. Okay, just see over here. When P1 has already put the S, the lock on S, P0 has put the lock on S, P1 has put the lock on Q. Can P0 again put a lock on Q? Or P1 can put a lock on over here? If both wants to enter into the critical section, but to enter into the critical section, they need to put the lock on S and Q. Suppose this is required. Then can they continue? Just look into this situation and say, can P0 or P1 can continue execution? Both are binary semaphore. Both are binary, S and Q are binary semaphore. I hope you must have remembered the wait function. Wait function is while S less than equals to 0, semicolon, S minus minus. And what is signal function? S plus plus. So while it is coming out, it will increment the value of S. and while it is a wait function, it will check for while s less than equals to 0. If it is doesn't satisfy, then s minus 1. Now just look over here. When weight of s it will apply, suppose P0 will apply s. So s becomes what? S becomes 0 because s is 1. 1 doesn't condition doesn't satisfy, it will make it 0. At the same time, q will make it 0. Suppose P1 wants to execute, so P1 q will become 0. Now when P0 wants to apply the wait function, what will happen? So it will call the wait function while s less than equals to 0. So what does it mean? Condition satisfies or not? Wait of q means wait function will be called. What is there in the wait function? While s less than equals to 0, condition satisfies or not? Is the condition satisfies? Hello? Hello? Are you getting me or not?
Yes.
So what is the value of q now then? What is the value of q? Here. In P0, what is the value of q? Q has already, we have already made it to 0. We have already changed to 0. So that means it is waiting while s less than equal to 0. So it is spinning or not? So it is waiting over here. This will come to wait state. Now P1, it tries to acquire the lock over s. What is the value of s? 0. So it is also in waiting state. So both will be both will be in the busy waiting state, and none of them can enter into their critical section. This situation is known as the deadlock. So if we are not using the wait functions properly, that they may lead to deadlock. They may lead to deadlock. There is another concept called the starvation. There is another concept called starvation. Starvation is known as the indefinite blocking. Starvation is known as the indefinite blocking. A process, what is that starvation over here? It says that process wait indefinitely with the semaphore and it is not removed from the semaphore queue in which it is suspended. So what is the difference between this here in the starvation and deadlock? In deadlock, they will never continue. They will never continue because both are in the waiting state and waiting for each other to continue. That cannot be possible. Starvation says that even if it is ready, but it is not getting the chance to continue. But we cannot deny that it will never get a chance. So it may get a chance, but it is blocking for an indefinite period of time. So process wait indefinitely with the semaphore and it is not removed from the semaphore queue. It is not removed from the semaphore queue in which it is suspended. There is another concept called priority inversion. Scheduling problem when lower priority process holds a lock needed by higher priority process. Lower priority process holds a lock needed by higher priority process. This is being solved by priority inheritance protocol. We use that. We have a priority inheritance. We'll read it in detail in our deadlock chapter. But for the time being, you remember deadlock in which the processes could not continue because they are waiting for each other for their execution. Starvation is indefinite blocking, but we cannot. We are not saying that they will never execute, but they are being suspended or they are being blocked for indefinite period of time because of priority schedule. Is it understood or not? There are some classical problem of synchronizations. These three problems are very, very important, and definitely one of these three problems may come in your exam as well. the classical problem used to test newly processed synchronization schemes. So there are some classical problems which are already designed. We will discuss them. Bounded buffer problem, reader writer problem, dining philosopher problem, and sleeping barber problem. Sleeping barber problem is not in your course. So we are discussing about this bounded buffer, reader writer, and the dining philosopher problem. So coming to the first one is the bounded buffer problem. Bounded buffer problem is also known as the producer consumer problem. This is also known as the producer consumer problem. Correct? I'll go for the bounded buffer problem. So listen it carefully. First thing is that what is bounded buffer problem? Bounded buffer problem is also known as producer consumer problem. Correct? We have a buffer which has a fixed limit. We have a fixed limit. We say it's a bounded. Suppose I will say 10 slots are there, 10 buffers are there. So that means 10 items can be produced. 10 items can be produced. Correct? And so here in producer consumer problem or bounded buffer problem, there is a producer, there is an entity called producer, there is another entity called consumer. Listen it carefully. There are two entities. One is producer, which go on producing the items. There is a consumer which continuously consumes the items. There are some fixed slots in which the producer produces and put the item. The consumer also takes the item from those slots. We must ensure that while a item is produced, at the same time the consumer cannot take. The item will be produced, it will be informed to the consumer that one more item is produced, you can take. Correct? Just I am giving an example of in a restaurant. Let's take about a bakery shop. In a bakery shop, the cakes are being made. Cakes are being made in a bakery shop. So think of this is the belt in which the cakes are need to be placed. So we have some places over there where the cakes are being prepared and it has to put on these slots. Correct? So we have some slots over here. So we have taken 5 slots. So what is the bound on my what is the bound over here? I have 5 slots over here only. So one end is the producer. Think of this end, the bakery, the cakes are being prepared by the producer. In another end, there is a consumer which takes the cakes from these slots. What is the maximum number of cakes the producer can produce at a time? How many cakes? How many cakes can be produced at a time? Anyone? Hello?
Sir, your voice is breaking. Can you repeat again?
Suppose this is in a bakery shop, we have a producer which is continuously producing the item. There is a consumer which consumes the item, or the waiter who is taking this item from these slots. Here I have some slots over here, 5 slots over here. Producer producing, putting in these slots, and consumer is taking. How many items the producer can produce maximum?
5.
5. So here my number of slots are 5. So producer can produce 5 items. So here if n is equal to 5. Correct? We must ensure that while a producer is producing, same time consumer cannot consume. Correct? So before producing, it will put a lock. While taking out, it will put a lock. Okay. Now second thing is that producer must produce fast, then the consumer must take. Can a consumer take before producer? It is not being produced. So producer must produce fast, then the consumer must take. So consumer has to wait till the producer has not been finished. Item is not being finished. So there are n number of buffers, n number of slots are there, right? So buffer is set of memory location where data stored temporarily. Size of the buffer is limited to finite. So there are n buffers. There are n buffers. In our case, it is 5. Each can hold one item. So at a time, only one user is allowed to access the buffer. Either the producer or consumer can have access to this buffer. Correct? Now, to solve this problem, we require 3 semaphores. We require 3 semaphores. That means 3 integer variables we require, which will be shared by both producer and consumer. What are those? One is mutex, another is full, third one is empty. So to this data buffer, there are number of slots are over here. There are number of slots in this data buffer. The producer is producing items and consumer is taking items from these buffers. Now, as I said, when at a particular time, suppose it wants to access this slot, either the producer or consumer must have access. So before accessing, it must put a lock, and after accessing, it must release the lock. And for this, we need a variable that is mutex. Mutex is counting variable or binary counting semaphore or binary semaphore. I have already told mutex is binary semaphore. So it will put a lock and release a lock. So when a consumer will take the item, it will put a lock, consume it, and release the lock. This is over. So first condition satisfied. Second on what I said, whenever a producer will produce an item, suppose the item is produced, it must inform the consumer that the item has been produced. It's like the producer, the person who is baking the cake. He will say that, hey, one item, one cake is produced. You can take, you can consume it. So how it will know? By incrementing the full slot. So full is actually 0. One item is produced, full becomes 1. Then another item is produced, full becomes 2. So it is a counting semaphore, and it can count up to maximum n. So full is initially all are empty. So full is 0. So full is 0. Every time a producer produces an item, full is incremented to 1. And similarly, one more counting semaphore will take, that is called the empty. Empty is initialized to what? Empty is n. That means all are empty initially. It is initialized to n. Whenever one item is consumed, the empty will be decremented. Is it understood? 3 semaphores we have taken. One is mutex, which will be these. Remember, as these are semaphores, these are shared by producer and consumer. This will be shared by producer and consumer. Every time, whether it is a producer or consumer wants to produce an item or consume an item, before that, it will put a lock and release the lock. So we take a binary semaphore for the same, and that is mutex. Producer must inform that a item is produced to the consumer. For that, we have taken a counting semaphore full, which is initialized to 0. We take another counting semaphore empty, which is initialized to n. So this says that initially all are empty, none of them are full, and empty mutex is 1. This is our initialization. Correct? Now we'll see that what is the order we will put these 3 variables. What is the order in which we will put these 3 variables so that we can solve this problem. Just see over here. We have this is our producer and this is the consumer. This is the producer process and this is the consumer process. Right? What we have done, this is whenever a item is produced, this is the item produced. This is the item produced. So whenever we are producing an item, before that we'll put a lock, and after producing the item we'll release the lock. So wait mutex, item is produced, and signal mutex. What is wait mutex will do? Mutex is initialized to 1. So 1 s less than equals to 0 doesn't satisfy, s minus minus. So mutex will become 0 and it will enter. So at the same time, if consumer wants to enter, what is the value of mutex? Mutex is 0, right? So it has to wait over there. It has to wait over there. So I think these 3 lines are understood: wait mutex, item produced, signal mutex. Similarly for consumer, this is here it is removing an item from the buffer. So we put a lock wait mutex and signal mutex. I think these 3 lines are understood for both producer and consumer. Correct? So mutex use, any doubt?
Yes.
Okay, now whenever a item is produced, that means the full must increment. Whenever an item is produced, the full must increment or not. That means signal full, signal operation does what? S plus plus. So signal full we are doing. Why it is there? Because it must, a item must be produced, then only the consumer can take. So we have wait full over here. It is waiting for full. So the full is a semaphore, counting semaphore. So unless it is a positive value, it will not enter into the, it will not go to the next statement. So we have signal full. That means it is saying that some item is, the item is produced or full is incremented, and so that the consumer can, this condition will not satisfy because full becomes 1 or some positive value. So that less than equals to 0 doesn't satisfy and it will enter. Whenever the consumer will consume, after consumer will consume, it will make signal empty. Signal means what? Empty is incremented over here. Signal empty, right? And wait empty. Why it is wait empty? Because if all are full, the producer cannot produce more item, right? So whenever a consumer consumes, it gives a signal so that the producer can produce another item. Is it understood?
Yes.
This is an important problem. So go through this concept carefully. Maybe if you have doubt in the next class, you ask me again if you have doubt on this producer consumer problem or bounded buffer problem. Let me take the attendance for today. (13), 16, 16 is present, okay. 18, 20, 21, 22, 24, 25, 7, 29, 30, 44, 51, 56, 57, 73. Some of the students have not joined with their roll numbers. Manas Senapati, Swapnil Naik. Join first. Write your roll number, then.
Sir, 13 present.
13 present. Yes. So I am just calling the absent roll numbers. Roll number 2, roll number 18, 20, 18, 20, 18 is present now.
Sir.
Roll number 18 present.
Yes, sir.
20, 22, 24, 24 is present now. 25, 27, 29, 30, 37, 39, 43, 44, 43, 44, 51, 56, 57 is present now. Okay, 73. 57 present. 57 is present. Okay. So next class you come prepare by reading this producer consumer. I'll ask some questions from there and then I will continue the discussion. So I am just ending the session now.